Hello everybody. Previously we have discussed acid-base reactions. In addition to these, there is a second class of common reactions, which are the redox reactions. In this slide, you can see redox chemistry happening in nature. For example, you can have a fire that consumes, for example, trees. Or on the right side, you can see metals exposed to the elements being corroded. Now, corrosion and burning are examples of redox reactions, namely the reactions with oxygen. In order to understand redox chemistry properly, you need to understand the concept of oxidation states. Here we will define the oxidation states. The oxidation state of an element, regardless of its existence as atom or molecule, is taken as zero. For example, you have neon as a noble gas, or you have dihydrogen or phosphorus existing as a P4 molecule. In all these examples, the oxidation state is zero. Now, the oxidation state or oxidation number is defined as the charge that an atom in the molecule would have if the molecule consisted entirely of iron. Here we can see an example of a water molecule, and if we treat the water molecule as an entity consisting of ions, then we have to write H+, H+, and O2-. Now these H+ and O2- are the charges of the respective ions in a hypothetical ionic water molecule. And so we can assign the oxidation state +1 to the hydrogen moiety and the oxidation state of -2 to oxygen. There are conventions on how we write oxidation states. In formula, the oxidation state is indicated in superscripted Roman numerals after the element and after the plus or minus symbols. For example, we have an iron +2 species, which can be written as such with a +2 in Roman numerals. Or for positive oxidation states, we often drop the plus symbol, and you can also write it in this simple form. Sulfur -2 is an example for a negative oxidation state. On the other hand, when we write a text and we use the name of the element fully written, then the oxidation state is indicated in bracketed Roman numerals after the element name and after the plus or minus symbols. Here you can see again examples written as iron 2 or sulfur -2. And again, for positive oxidation state, we can choose to drop the positive sign. Take note that the charge is not the same as the oxidation state. So we have been dealing with charges here, which allowed us to determine oxidation state. But they are not the same. Charges are indicated in Arabic numerals and also in superscript after the element symbol or after the ionic unit, but they appear before the plus or minus symbols. For example, you have iron 2+ or sulfur 2-. And here you can see the charge is written with Arabic numeral followed by the plus and minus symbol. Here we have ionic entities or ionic units. And so the charge applies not just for a simple monoatomic ion, but also for ions consisting of groups of elements. Here we have ammonia plus, and we have also encountered previously a nitrate anion, which is written as NO3-. And the charge and oxidations number are only identical for monoatomic ions. And again, we have seen examples like this iron 2+, where the charge is 2+ and the oxidation state is also +2 because we are dealing with the ion which consists of only one atom. Now, how do we assign oxidation state? We have already seen how we assign the oxidation state for the elements of a water molecule. And here we will look at two more examples, for example, this particular molecule and the permanganate anion. Let's start with the H2S2O6. We know already from the water molecule that hydrogen in most cases is assigned a +1 charge. On the other hand, we also know that oxygen in most cases has a -2 charge. So therefore, we can calculate the oxidation state of the sulfur in this particular molecule. How do we do that? We have two hydrogen atoms in this molecule, so we can write 2 times H+ plus 2 times the oxidation state of sulfur, plus 6 times the oxidation state or the charge of oxygen. And since this whole molecule is neutral, the sum of all these should give rise to 0. And so if we actually do this calculation, we end up with the oxidation state of sulfur as being +5. We can also look at this example of the permanganate anion. And in this case, it's slightly easier. We have only manganese to consider, and we have 4 oxides. But in addition to that, we have a 1 negative charge. So X equals to 4 times O2 minus, which should give rise to a -1 charge left of this anion here. So if we again add in the -2 for the oxidation state of oxygen, then we end up with an overall oxidation state for the manganese of +7. Now these are inorganic molecules, so they are very easy to assign. How do we do that with organic molecules? So how do we assign, for example, the oxidation state of this particular carbon atom in the benzaldehyde molecule, or acetophenone molecule, or a benzoic acid molecule? Now, in order to do that, we only have to consider the neighbors or the direct substituents of this particular carbon atom. We can see in this particular example that this carbon atom is bound to another carbon atom here of the aromatic ring. It is also bound to a hydrogen, and it has 2 bonds to an oxygen. Now, all we need to consider is which element is more electronegative compared to the carbon, and which elements are more electropositive. In this example, we have hydrogen. So hydrogen is more electropositive. So you can assign a positive charge for this hydrogen. And since you are having 2 bonds to this oxygen, which is more electronegative than carbon, you can assign a 2 minus to this particular oxygen because there are 2 bonds. For this particular connection, this carbon is bonded to another carbon, and so they have the same electronegativity, which means this carbon does not contribute anything to the oxidation state of this particular carbon. So overall, we can say that this carbon has an oxidation state of 1. So if we look at the second example, again, it's very similar. Here we have 2 neighboring carbon atoms. So they do not contribute to the oxidation state, but instead we have only 2 bonds to a more electronegative element. Therefore, this carbon should have an oxidation state of +2. For the last example, we have actually 2 electron negative substituents directly at this carbon and 1 carbon substituent. This one again doesn't play any role in the determination. And we have 3 bonds to an electronegative element. So this carbon should have an oxidation state of +3. So here are again the oxidation state: carbon +1, carbon +2, and carbon +3. Knowing oxidation states, we can now move on and deal with oxidation and reduction reactions. Now, the oxidation is defined as a loss of electrons associated with an increase of the oxidation state or the oxidation number. Alternatively, you can also treat it as a loss of hydrogen atoms from a molecule or the gain of oxygen atoms in the molecule. An oxidizing agent or oxidant is a species that removes electrons from other species. On the other hand, reduction is the gain of electrons associated with a decrease of the oxidation state. Again, you can consider hydrogen atoms. So you can gain hydrogen atoms or you can lose oxygen atoms in the process of the reduction. A reducing agent or reductant is a species that provides electrons to other species. Overall, reduction and oxidation must appear together in a redox reaction. So a redox reaction combines reactions involving both reduction and oxidation. Here we can see a simple redox reaction. We are having 2 equivalents of magnesium that reacts with 1 molecule of oxygen to form 2 equivalents of magnesium oxide. In this particular example, magnesium in the oxidation state of 0 has been oxidized to magnesium 2+. So we can write it as a separate oxidation, whereby again an oxidation state of 0 has been converted into an oxidation state of 2+. So the oxidation means in this particular case that magnesium has lost 2 electrons. The oxygen molecule, on the other hand, is converted to 2 equivalents of oxide, O2-. And so in order to balance the charge here, you have to add 4 electrons on the left side. So oxygen or dioxygen in the oxidation state of 0 takes in 4 electrons to form 2 oxides. So we have a reduction, which means a gain of 2 electrons per oxygen atom. The magnesium oxide, by the way, is also a health supplement. And so when you lack magnesium, you can actually take pills that contain magnesium oxide. Since we are dealing with monoatomic ions in these two reactions, we can also conclude that the charge and the oxidation state are identical, but only in this particular example. If you want to see how magnesium reacts with oxygen, you can go to this particular YouTube video here, where they basically burn magnesium. And overall, burning means you have this reaction occurring. Since redox reactions involve the transfer of electrons, you can actually make a device that creates electricity. Here we see a very simple example, which is called the Daniell cell. On the right side, you can see a zinc foil, which means the element zinc, dipped into a beaker which contains a 1 molar solution of zinc 2 sulfate. And so what happens here is that the zinc 2 plus in the zinc 2 sulfate solution would establish an equilibrium with the zinc 0 in the zinc foil. So this equilibrium leads to a particular potential that builds up in this half cell. On the other side, you have a copper foil, which is also dipped in a copper 2 sulfate solution of a 1 molar concentration. Now what you have here is very similar. You have an equilibrium that establishes between the copper 2 plus ions in solution and the copper 0 in this particular foil. And again, you have a buildup of a certain potential. Now, if you connect these two foils with each other, then electron would flow from one side to the other side. In this particular case, the electrons would flow from the zinc to the copper cell. And in order to provide neutrality in terms of ion, you have this ion bridge. Overall, since electrons are flowing from the zinc cell to the copper cell, it means that the zinc foil loses electrons, and so this foil will be smaller and smaller because the zinc foil essentially dissolves and you have more and more zinc 2 plus ion in solution. And on this side, you have more and more copper 2 plus ions that gain the electrons to add onto the foil, and so this foil will become bigger and bigger. Overall, you have an equation which looks like this. You have copper 2 plus from this particular solution here that gains the electrons from the zinc foil to form elemental copper, and the zinc foil loses 2 electrons to form zinc 2 plus ion that then obviously becomes equated and go in solution. That was a very simple redox equation. Let's look at a more complicated example and analyze this example in terms of understanding how it works. So we can consider the following redox reaction where 16 equivalents of hydrochloric acid reacts with 2 equivalents of potassium permanganate to form 5 equivalents of chlorine gas, 2 equivalents of KCl salt, and 2 equivalents of manganese chloride salt. In addition, 8 molecules of water are also liberated. Now, the first thing you do is to analyze oxidation state. And so you need to figure out which participants has been oxidized and which participants have been reduced. We will just go ahead and analyze this. And so in HCl, we know that the chloride should be 1 minus because the proton or the H is 1 plus. So Cl is assigned a 1 minus charge. In this particular case, also 1 minus oxidation state. And it has been converted to a chlorine molecule, which has an oxidation state of 0. So this is representative of chlorine as the element. So if you follow the red line here, you know that an oxidation state of -1 has been converted to an oxidation state of 0. So the chloride has lost an electron, which means it has been oxidized. And since you are having 5 molecules of chlorine, you have to lose essentially 10 electrons, which means 10 times +1. Having identified the oxidation half reaction, we need to figure out which one is in charge for the reduction. So again, we do the same thing. We will assign oxidation state. And so in this particular potassium permanganate moiety, we can assign a +7 oxidation state to the manganese in permanganate. On the right side, you have actually manganese chloride. And so you also know immediately manganese should have a 2 plus charge, which translates to a +2 oxidation state. So to convert a +7 oxidation state to a +2 oxidation state, you need to gain 5 electrons. So this is the reduction, and you need to gain 5 electrons for each manganese atom. Since we are having 2 manganese atoms that have been converted, we have to consider 2 times -5 for our reaction. So overall, the net change in oxidation state for the oxidation and reduction steps in a given redox reaction must be balanced. In this particular case, we have both times 10 electrons that has been given from the chloride to the manganese. In the previous example, we could identify the oxidation and the reduction according to the changes in oxidation state of a particular species in the equation. But if we are given just reactants with the purpose of establishing an equation, how do we know which species is acting as an oxidant and which one is acting as a reductant? In order to know that, we need to understand reduction potentials. This slide demonstrates how a reduction potential for a specific reagent is determined. The setup to determine this is very similar to the Daniell cell or Daniell element that we have already discussed. On the left side, you can see a platinum electrode which is immersed in a 1 molar solution of protons. In addition, there is this tube which provides hydrogen gas that bubbles on top of this platinum electrode. So on this particular surface, you have an equilibrium established between the protons in solutions, the H+, and the dihydrogen gas that bubbles onto this platinum foil. So overall, you have this equation whereby 2 protons receive 2 electrons to form dihydrogen. So this creates some sort of potential that builds up on this particular cell. It is important to consider that we have a gas pressure of 1 bar of dihydrogen that passes through this tubing into the cell and out again. Also, we need a 1 molar acid concentration. With these, we have standard conditions, and this particular cell on the left side is called the standard hydrogen electrode. And empirically, people have set the potential of this particular cell as 0 volts. And then you can put various different half cells and connect it to this particular standard hydrogen electrode. And the potential that builds up is then the redox potential of the particular cell in consideration. In this example, we are looking at the zinc cell. So zinc foil, just like in a Daniell cell, is dipped in a solution of 1 molar zinc 2+ ion. And in this cell, you have again this equilibrium that forms between the zinc 2+ ion and the zinc foil. And if you would connect these two half cells with each other and you would measure the voltage, then you can measure a voltage of minus 0.76 volts for this particular cell. Now, I forgot to mention that the temperature here must be constant and must be kept at 298 kelvins. And so you have standard conditions. Now, if you allow the electrons to freely flow from one cell to the other side, then you have this overall equation. Zinc solid or zinc element reacts with 2 equivalents of protons to form zinc 2+ and 1 molecule of dihydrogen. For this particular reaction, you can then determine the delta E, which means you are taking the standard hydrogen electrode 0 volt and you deduct the potential of the zinc cell, which is minus 0.76 volts, and that overall gives a positive value. So the delta E is actually positive 0.76 volts, and that is the standard electromotive force. Now, if the delta E is positive, that means that the reaction is preferred, and eventually the zinc foil would dissolve into this solution here, and all the electrons would be pumped over to this side where the protons are reduced to dihydrogen. Now, this is just a setup for a zinc cell. You can now do many different other cells and compare that to the standard hydrogen electrode to measure their standard reduction potentials. This has been done, and here you can see a table that summarizes selected examples. Here in red, you can see our standard, namely the reduction of protons to dihydrogen. And all the cells that appear above this standard would have a positive value. And in this direction, you have an increasing power of oxidant. On the other hand, you have smaller values than 0, which means negative values. And if you go down here, you have an increasing power of reductant. In this slide, I have also highlighted 2 examples in blue. So we have a process involving, again, the permanganate anion that is reduced to a manganese 2+, and we have a calcium cell, which consists of calcium plus being reduced to calcium solid. Now, another important thing to note is that these reduction potentials, as the name suggests, are always written in the form of a reduction. So you always have the gain of electrons in this particular equation, which leads to a reduced species on the right. So these values are always indicative of this particular reaction in this particular direction. So let's consider these two examples highlighted in blue, and let us construct a reaction involving them. Since the permanganate cell has a more positive value compared to the calcium cell, this one will be the oxidant. So we can extract these two equations and write them under each other. Again, we have here permanganate anion, which forms manganese 2+, and we have a calcium 2+ ion that forms calcium. Now, the first thing we need to do is to identify the number of electrons being transferred. So this is already depicted here. We have 5 electrons being transferred in this particular reaction, and we have 2 electrons in this reaction. So we have to make sure that the number of electrons that exchange are equal. And so we can multiply the first reaction by 2 and multiply the second reaction by 5 to get 10 electrons. So let's do that. So the first reaction has been multiplied by 2 permanganate anion reacting with 16 equivalents of protons and 10 equivalents of electrons to give 2 equivalents of manganese 2+ ion and 8 equivalents of water molecules. On the other hand, you have 5 equivalents of calcium 2+ that reacts with 10 electrons to give 5 equivalents of calcium. The next step is to combine these two equations. Now the calcium has a lower redox potential, and so it will be the reductant. It will reduce the permanganate to manganese 2+ by giving each of the manganese ion 5 electrons. In order to combine these two, we have to basically deduct the second equation from the first equation. Or we can also invert this second reaction and add it to the first reaction. That has been done here. And so we have this final result whereby 2 equivalents of permanganate reacts with 16 equivalents of protons and 5 equivalents of calcium to give 2 equivalents of manganese 2+, 8 water molecules, and 5 calcium 2+ ions. Now in this equation you can see also that permanganate gains 5 electrons from the calcium to form the manganese 2+, whereby the calcium has been oxidized to calcium 2+ ion. So do not forget that the equations must always be fully balanced. In the previous example, we have seen that the oxidant and reductant are derived from different elements. Now sometimes you also have a scenario in which the oxidant and reductant are derived from the same element. Here we can see 2 copper 1 being simultaneously oxidized to copper 2 and reduced to elemental copper. And this particular reaction is a disproportionation. If we look at the individual half reactions, we can see that the reduction of copper plus to copper 0 has a standard reduction potential of positive 0.52 volts. And we can also see the reduction of copper 2+ to copper 1+ has a positive value of 0.16 volt. Now again, for this particular reaction, we can form the electromotive force. And if you do so, you realize that the EMF has a positive value of 0.36 volts. Having a positive value means that this reaction is actually favorable. And so indeed, if you have copper 1 ions present, they would disproportionate to copper 2+ and copper 0. So this particular reaction again is called a disproportionation. Another example of a disproportionation is the hypochlorous acid. Here we have an example. 5 equivalents of hypochlorous acid would react to form 2 equivalents of chlorine and 1 equivalent of chlorate. In addition, you have water molecules and protons that are needed in the equation to fully balance it. So the disproportionation is a redox reaction in which the oxidation number of an element is simultaneously raised and lowered. The reverse reaction is also known, and that is called a comproportionation. Here is an example. We have 1 equivalent of silver 2+ reacting with 1 equivalent of silver element to form 2 equivalents of silver 1+. And this particular reaction has an EMF of positive 1.18 volt. And again, being positive means that this reaction is indeed favorable. So let's look at a simple energy profile of a redox reaction. Again, we are using the Daniell cell or the Daniell element as an example. And before the reaction, you have zinc solids reacting with copper 2+ ion to form zinc 2+ ion and copper solids. Now, the free Gibbs energy of the products must be more negative compared to those of the reactants before the reaction. In order to quantify the free Gibbs energy, you can use this particular equation. Delta G, which is the Gibbs free energy, equals to minus NF, whereby N is the number of moles of electrons being transferred. F is simply the Faraday constant multiplied by delta E naught, which is the electromotive force. So delta E is very useful in predicting whether a redox reaction is thermodynamically favorable or not. And overall, a reaction is favorable when delta G is negative, which in other words means that delta E should be very positive. So again, here are the descriptors of these particular parameters. You can also relate the free Gibbs energy to the equilibrium constant by considering the second equation we have also seen previously already. So in this equation, we are relating the Gibbs free energy to the equilibrium constant, whereby R is the ideal gas constant, T is the temperature in Kelvin, and K is our equilibrium constant. So overall, we can conclude as delta E becomes more positive, delta G becomes more negative. And if we relate that into this equation, we also know if delta G becomes more negative, K must increase. Thus, the reaction is thermodynamically more favorable when delta E is more positive. Let's look at an example of the redox couple involving magnesium and copper. So you should calculate the free energy change, delta G, and the equilibrium constant K for the following reaction. Magnesium reacts with copper 2+ to form copper as an element and magnesium 2+. Now you can look up in the previous table that this particular redox potential has a value of 0.34 volts. The respective magnesium value is minus 2.37 volts. And so you can calculate the EMF or delta E by doing a subtraction of the second equation, which has a more negative value, from the first equation. Overall, you have this process and you have a delta E of positive 2.71 voltage, which means this is a very favorable process. Now you can use this delta E to feed into the equation. And you also know that we are transferring in this reaction two equivalents of electrons, so N equals 2, and that is factored in here. And this is our delta E value. So after input of the Faraday constant, you can basically calculate that delta G is minus 522 kilojoules per mole. Now you can use the second equation, which relates delta G to K, and you can get a value of 3.2 times 10 to the power of 91. And so this K is huge, which means this is a very favorable reaction. This slide demonstrates again what we mean with subtraction of equations. If you have two equations written in the reduction form, then if you want to subtract the second equation from the first, you can reverse this reaction and just simply add it together. And here we have a more specific example involving numbers. You can just go through that yourself and practice that on your own. So far, we have looked at redox reactions that are occurring under standard conditions, which means in all these cases, we were using standard reduction potential, and that would imply that our solutions are always 1 molar in concentration. The question is, how do we deal with reactions that deviate from the 1 molar concentration? This question brings us to the Nernst equation. And the Nernst equation was named after Walter Hermann Nernst, who was a German physical chemist born in 1864 and died in 1941. He won the Nobel Prize in Chemistry in 1920. And he defined this equation whereby you can relate a reduction potential to the concentration of the species involved. And so you have E equals the standard reduction potential minus RT divided by NF. And again, N is the number of electrons being transferred in this particular reaction, multiplied by the natural logarithm of the reduced form over the oxidized form. Now, when the concentration of the reduced form and the oxidized form are both 1 molar, then E will become the standard reduction potential that we have been already using in the previous reactions. So here we look at a concentration dependence of the redox potential. And as an example, we can calculate the copper 2 plus copper redox potential for a 10 molar solution of copper 2 plus. The reduced form in this particular cell will be obviously elemental copper. And so the elemental copper is a solid, which means its concentration can be set as 1. For the oxidized form, we have copper 2 plus ions, and it's indicated in the question that we have a 10 molar solution. So the concentration of the copper 2 plus solution will be 10 molar. The number of electrons being transferred from copper 2 plus to give copper is 2, so N equals 2. And so we can use the Nernst equation to calculate the reduction potential of a 10 molar solution of copper 2 plus. And that is demonstrated here. The standard reduction potential of this cell is 0.36 minus 0.03, and that gives rise to 0.39 volts, which is essentially larger than the standard reduction potential. So the redox potential increases with concentration. Here we have another example in which we calculate the redox potential of our permanganate manganese 2 plus cell at a pH of 2.5. For simplicity, we just take the concentration of the permanganate ion and the manganese 2 plus ion as 1 molar. So overall, we have this particular equation again. We have permanganate reacting with 8 equivalents of protons and 5 equivalents of electrons to form the manganese 2 plus ion and 4 equivalents of water. This has a standard reduction potential of 1.51. So this we can actually feed into this equation. And we have the gas constant, the temperature, which shall be 298 Kelvin. We have 5 electrons being transferred, so N equals 5. And Faraday constant is also known. And so this concentration is equal to 1. The permanganate concentration is also 1. And the concentration of the protons we can obtain from the pH value by reversing the negative log. So if you do that, then you have this particular value. And since the permanganate and manganese 2 plus concentration is 1, all you have left is to consider this particular value to the power of 8. And when you do this calculation, you will come up with 1.27 volts. So overall, you can say that the permanganate becomes less oxidizing as the pH increases. So this value, again, is smaller than this one, which is at pH 0. And so at higher pH, the oxidizing power becomes less. Now with this slide, we will close our first lecture on redox chemistry.